Right. Rethinking model scaling through convolutional convolutional methods are commonly developed at a fixed resource budget, and then scaled up for better accuracy if more resources are available. In this paper, we systematically study model scaling and identify that carefully balancing network depth, width, and resolution can lead to better performance. Based on this observation, we propose a new scaling method that uniformly scales all dimensions of depth, width, resolution using a simple yet highly effective compound coefficient. We demonstrate the effectiveness of this method in scaling at global widths and regions. To go even further, we use neural architecture search to design a new baseline method and scale it up to obtain a family of lines called EfficientNets, which achieve better accuracy and efficiency than previous column nets. In particular, our EfficientNet B7 achieves state-of-the-art 84.3 top-point accuracy on image, while being 8.4 times smaller and 6.1 times faster on inference than the best existing column net. Our EfficientNets also transfer well and achieve state-of-the-art accuracy in cipher 100, 91%, and flowers 98.8%, and 3 other transfer learning datasets with an order of magnitude fewer parameters, source code available at Introduction. Scaling of common nets is widely used to achieve better accuracy. For example, ResNet can be scaled up from ResNet 18 to ResNet 200 by using more layers. Recently, GPipe achieved 84.3 ImageNet top-1 accuracy by scaling at a baseline level 4 times that. However, the process of scaling at column nets has never been well understood, and there are currently many ways to do it. The most common way is to scale up column nets by their depth. Another less common but increasingly popular method is to scale up models by image resolution. In previous work, it is common to scale only one of the 3 dimensions, depth, width, and image size. Though it is possible to scale 2 or 3 dimensions arbitrarily scaling requires tedious manual tuning and still often needs suboptimal accuracy and efficiency. In this paper, we want to study and rethink the process of scaling up components, particularly investigate the central question: is there a principled method to scale up components that can achieve better accuracy and efficiency? Our empirical study shows that it is critical to balance all dimensions of network width, depth, resolution, and surprisingly, such balance can be achieved by simply scaling each of them with constant ratio. Based on this observation, we propose a simple yet effective compound scaling method. Unlike conventional practice that arbitrarily scales these factors, our method uniformly scales network width, depth, and resolution with a sort of fixed scaling coefficient. For example, if you want to use 2 to the n times more computational resources, then we can simply increase the network depth by alpha to the n, width by beta to the n, and image size by gamma to the n, where alpha, beta, gamma are constant coefficients determined by a small grid search on the original small model. Figure 2 illustrates the difference between our scaling method and conventional methods. Figure 2. Okay. baseline, we have resolution, height times weight, layer I, channels, number of channels. Okay. Model scaling. A is baseline network. B to B are conventional scaling that only increase one-dimensional network with resolution. B is our proposed compound scaling method that uniformly scales all three dimensions with a fixed ratio. Width scaling. Width scaling. Okay. Width is in like how many channels, right? Yeah, how many number of channels. Width scaling is adding new limits, okay? Resolution scaling, okay? Compound scaling, all three. Okay, what is figure 1? Okay. Figure 1, middle size versus original accuracy. All numbers are for single craft, single line. Our EfficientNet significantly outperform other nets. Particularly EfficientNet V7 achieves new state-of-the-art 84.3% accuracy being 8.4 times smaller and 6.1 faster than G-Pipe. EfficientNet V1 is 7.6 smaller and 5.7 times faster than Resonate 153. Details are included 2 and 4. Let's continue. Intuitively, the compound scaling method makes sense because if the image is bigger, then the method needs more layers to increase the effective field and more channels to capture more fine-grained patterns on the bigger image. In fact, previous theoretical and empirical results both show that there exists certain relationship between network width and width. But to our knowledge, we are the first to empirically quantify the relationship among all three dimensions of network width, and resolution. We demonstrate that our scaling method works well on existing bigger nets and these nets. Notably, the effectiveness of model scaling heavily depends on the baseline network. To go even further, we use neural architecture search to develop a new baseline network and scale it up to obtain a family of models called EfficientNets. Figure 1 summarizes the internet performance where our EfficientNet significantly outperform our current nets. In particular, our EfficientNet V7 surpasses the best existing G-Pipe accuracy, but using 8.4 times fewer parameters and running 6.1 times faster and on inference. Compared to the widely used Resonate 50, our EfficientNet V4 improves the top-line accuracy from 76.3 to 83.0 plus that's a net positive 6.7% with similar plots. Besides image EfficientNets also transfer well and achieve state-of-the-art accuracy on 5 out of 8 widely used datasets, while reducing parameters by up to 21 times than existing convents. Related with convent accuracy, since AlexNet won the 2012 ImageNet competition, convents have become increasingly more accurate by 40 million, while the 2014 image in a billion achieves 74.8.1 accuracy with about 6.8 million parameters. The 2017 image in 7 achieves 82.7% top one accuracy with 145 million parameters. Recently, G-Pipe further pushes the art specifically of ImageNet top 1 validation accuracy to 84.3% using 557 million parameters. It is so quick that it can only be trained with a specialized pipeline paralleling library by partitioning the network and spreading each part to a different accelerator. While these memories are mainly designed for ImageNet, recent studies have shown better ImageNet models also perform better across a variety of transfer learning datasets and other different tasks such as object detection. Although higher accuracy is critical for many applications, we have already hit the hardware memory limit, and thus further accuracy gain needs better efficiency. Convnet efficiency. Deep convnets are often over-parameterized. Model compression is a common way to reduce model size by trading accuracy by efficiency. Also, as mobile phones become ubiquitous, it is also common to handcraft efficient model size convnets such as SpeedNets, MobileNets, and ShuffleNets. Recently, neuroarchitecture search becomes increasingly popular in designing efficient model size convnets and achieves better efficiency than handcrafted model convnets by extensively tuning the network with transmission kernel types and sizes. However, it was unclear how to apply these techniques for larger models that have much larger design space and much more expensive tuning costs. In this paper, we aim to study model efficiency for super large convnets that surpass state-of-the-art accuracy. To achieve this goal, we resort to model scaling. Model scaling. There are many ways to scale a convnet for different resource constraints. Those nets can be scaled down or up by adjusting network depth, not number of layers, while wide nets and mobile nets can be scaled by network width, number of channels. It is also well recognized that bigger input image size will help accuracy with overhead of more flops. Although prior studies have shown that network depth and width are both important in convnets' expressive power, it still remains an open question on how to effectively scale a convnet to achieve better efficiency and accuracy. Our work systematically and empirically studies convnet scaling for all three dimensions of the network width and resolution. Compound model scaling. In this section, we will formulate the scaling problem, study different approaches, and propose our new scaling method. Problem formulation. A convnet layer I can be defined as function yi equals fi of xi, where fi is the operator and yi is the output, and so xi is the input piece. With tensor shape hi, wi, ci, and for simple conditioning and batch dimension, okay. Hi and wi are spatial dimension, and ci is the channel dimension. A convnet N can be represented by a list list of composed layers. Composite and be the percent that list of composed layers. Okay. Practice components are often partitioned into multiple stages, and all layers in each stage share the same architecture. For example, Rosmix has 5 stages, and all layers in each stage has all layers have the same combination of time, except the first layer to performs bound segment. Therefore, we can define coordinates as I1 to S F I L I. Okay, where F I L I denotes layer F I repeated L I time in stage I. Okay. Figure 2A illustrates a resonant coordinate where the spatial dimension is gradually shown, but the channel dimension is expanded over layers. For example, from initial input shape 224, 224, 3 to final shape output 7754. Unlike regular coordinate designs that mostly focus on finding the best layer architecture Fi, model scaling tries to expand the network length Li, width Ci, and or resolution H and Wi without changing F predefined in the baseline method. By fixing F, model scaling simplifies the design problem for new resource constraints, but still remains a large design space to explore different L, C, H, and W for each layer. In order to further reduce the design space, we restrict that all layers must be scaled uniformly. In order to further reduce the design space, we restrict that all layers must be scaled uniformly with concentration. Our target is to maximize the model accuracy for any given resource constraints, which can be formulated as an optimization problem. Maximize accuracy, okay, such as this writing it in a fancy way. Let's just do like it doesn't make any sense because we didn't have any way to actually calculate these aside from knowing what if R stands for. Yeah. The W or the function scaling network. So H and W multiplied with R for resolution. D is multiplied with depth. W multiplied with channel. Okay. Where WD are coefficients for K network with resolution. To define parameters, okay. Scaling dimensions. Okay, long paper and still have not gotten anything out of it. Why do they have to write so long papers that can be Okay, 2 pages, and then charts, and that's it. Okay, 3 pages total. Each everyone has it. Okay. EfficientNet B0 ratio. Each row describes a stage I with NI layers with input resolution HI, WI, and output channels CI. Locations are adopted in equation 2. What is NB-con? Run through that lead. Make sure that's NB-con first. So this is the repetition. How many repeated? Yeah, what is stage 1? Okay, then get times. 1,200. Does it feel again? Scaling relations. The main difficulty problem to it is that the optimal V, W, and R depend on each other, and the values change under different resource constraints. Due to this difficulty, conventional methods mostly scale coordinates in one of these dimensions. But concept is the most commonly used by many coordinates. The intuition is that the deeper coordinates can capture richer and more complex features and generalize well on new tasks. However, deeper networks are also more difficult to train due to the branching in the problem, although several technologies such as script connections and batch parallelization alleviate the training problem. The accuracy gain in very deep network diminishes. For example, ResNet 1000 has similar accuracy as ResNet 101, even though it has much more layers. Figure 3 level shows our empirical study of scaling a baseline model with different subscription, further suggesting the diminishing accuracy return for very deep comments. Figure 3 level. Okay. Scaling up a baseline with different with good resolution or coefficients. Bigger networks with larger width or resolution tend to achieve higher accuracy, but the accuracy will quickly saturate after reaching 80%, demonstrating the limitation of single-dimensional scaling. Baseline network is described in Table 1. Here. This is doubling 8 times. Yeah, that's. But scaling network is commonly used for small size models. As discussed in wider networks tend to be able to capture more fine-grained features and are easier to train. However, extremely wide but shallow networks tend to have difficulty in capturing higher-level features. Our empirical results in Figure 3 left show that accuracy quickly saturates when the network becomes much wider with larger data. Quickly saturates. Is that the case? Yeah. Resolution. With high resolution input images, coordinates can potentially capture more fine-grained patterns starting from 224 by 224 in early coordinates. Multi-coordinates tend to use 299 by 299 for better accuracy. Recent VG achieves state-of-the-art imaging accuracy with 480 by 480 resolution. Higher resolutions such as 600 by 600 are also widely used in object detection. Coordinates Figure 3 right shows the result of scaling network resolutions, where indeed higher resolutions improve accuracy, but the accuracy gain diminishes for very high resolutions. R equals 1 denotes resolution 2.4 by 2.4, R 2.5 denotes 560 by 560. The above analyses lead us to the first observation. Observation 1. Scaling of any dimension of network with all resolution improves accuracy, but accuracy gain diminishes for bigger models. Okay. Compound scaling. When paired with where different scaling dimensions are not independent, intuitively for higher resolution images, we should increase network depth such that larger receptive field can help capture similar features that include more pixels and bigger images. Correspondingly, we should also increase network width when the resolution is higher. Correspondingly, we should also increase network width when the resolution is higher in order to capture more fine-grained patterns with more pixels and high-resolution images. These intuitions suggest that we need to coordinate and balance different scaling dimensions rather than coefficient scaling or conventional single-dimension scaling. To validate our intuitions, we compare width scaling under different network widths and resolutions as shown in Figure 4. If we only scale network width W without changing depth D equals 1 and resolution R equals 1, the accuracy saturates quickly with deeper D equals 2 and higher resolution equals R equals 2. Width scaling achieves better accuracy under the same flex cost. These results lead us to the second observation. Observation 2. In order to pursue Data accuracy and efficiency. It is critical to balance all dimensions of network depth and resolution during complex scaling. In fact, a few prior works have really tried to arbitrarily balance network width and depth, but they all require tedious manual tuning. In this paper, we propose a new compound scaling method, which will use a compound coefficient phi to uniformly scale network width and resolution in a principal way. Depth equals alpha to the phi, width equals beta to the phi, resolution R equals gamma to the phi, such that alpha times beta squared times gamma squared is almost equal to 2. Alpha greater than 1 equal to 1. Beta greater than equal to 1. Gamma greater than equal to 1. Where alpha, beta, gamma are constants can be determined, so it doesn't support scaling down, only scaling up a bit. Where alpha, beta, gamma are constants that can be determined by a small group set. Intuitively, phi is a user-specified coefficient that controls how many more resources are available for scaling, while alpha, beta, gamma specify how to assign these extra resources to network depth and resolution, respectively. Notably, the flux of a regular convolution operation is proportional to d w squared r squared, i.e. w network depth will double flux, but doubling network width or resolution will increase flux by 4 times. Since convolution ops usually dominate the computation cost and convolutes, scaling a convolute will approximately increase total flux by alpha, beta squared, gamma squared, phi to the phi. In this paper, we constrain alpha, beta squared, gamma squared, the product of these to equal approximately 2, such that for any new phi, the total flux will approximately increase by 2 to the phi. Okay. Flux may differ from theoretical value due to the efficient net architecture. Since modern scaling does not change lower operators Fi in baseline network, having a good baseline network is also critical. We will evaluate our scaling method using existing convolutions. But in order to better demonstrate the effectiveness of our scaling method, we also developed a new model-sized baseline called EfficientNet. Inspired by Dan and L 2019, we developed our own baseline network by leveraging a multi-objective neural architecture such that optimizes both accuracy and flux. Specifically, we use the same search space as done in L 2019 and use accuracy times flux over T over W as optimization goal, where accuracy N and flux N denote the accuracy and flux of the model N. P is the target flux, and W is minus 0.07. Is our parameter for controlling trade-off between accuracy and flux. Unlike time law, we here we optimize flux rather than latency, since we are not targeting any specific hardware device. Our search procedure produces an efficient network, which we name EfficientNet VNet, since we use the same thread space. The architecture is similar to many to NMAS, except our efficient VNet is likely directly to the larger flex target. Our flex target is 400 million. Table 1 shows our architecture efficient VNet. It is main building block is mobile inverted battery conjugate NB conjugate, okay, to which we add mobile inverted battery NB conjugate, okay, to which we also add speed and excitation optimization. Starting from the baseline efficient net VNet, we apply our compounding scaling method to scale up these steps. Step 1. We fix phi equals 1, assuming twice and more resources available, and do a small group search in alpha, beta, gamma, based on equation 2 and 3. In particular, we find the best values for sufficient alpha 1.2, beta 1.1, gamma 1.15 under constraint of okay. Step 2, we fix alpha, beta, gamma constant and scale up the baseline using to different phi using equation 3 to obtain efficient net B to 7 or B1 to B7. Okay. Notably, it is possible to achieve better performance by searching for alpha, beta, gamma directly around a large model, but the search cost becomes prohibitively more expensive on larger models. Our method solves this issue by only doing search once on small baseline method, step 1, and then use the same scaling coefficient for all other models, step 2. Parents, in this section, we will first evaluate our scaling method on existing coordinates and the new proposed efficient nets. Scaling up global nets and resonance. As a proof of concept, we first apply our scaling method to the widely used narrow nets and ResNet. Table 3 shows the ImageNet results of scaling them in different ways compared to the single dimension scaling method. Our compound scaling method improves the accuracy of all these models, suggesting the effectiveness of our proposed scaling method for general existing coordinates. Table 3, right? Table 3 compound scale, compound scale, compound scale. Okay. Interesting. We didn't mention the compound scale here. Be right back. Okay. Let's go back. And then get results for EfficientNet. We train our EfficientNet models on management using similar settings as time ago. I'm supposed to optimize it. When we go down 0.9, momentum 0.9, backstrong momentum 0.99. ATK 1.8, oh, 800 degrees by maybe 2.4 epochs. Personal activation, auto admin, auto admin. Stochastic depth, divided probability 8.8. Bigger models gain more generalization. We linearly need to increase dropout from 0.2 for EfficientNet B0 to 0.5 for B7. We reserve 25 kilogram negative images from a training set and a mini down set and perform early stopping in this mini down. We then evaluate the early stop checkpoint on the original validation set to report the final validation accuracy. Table 2 shows the performance of all EfficientNet models that are given these all of them use fewer parameters than other candidates. Like this, in particular, EfficientNet B7, A4, okay. Okay. Repeating the same symbols over and over. Thanks for learning. Okay. That's it. Nothing more than this paper other than, well, this is the relation and this is the equation, and that's it. Okay. I'll check the other resources and see if I get anything more useful.